So what we're doing is setting a foundation in preparation for similar shapes by talking about the various transformations. There are 4 transformations we're going to deal with. 3 of them are what are called rigid transformations, which means that, for instance, if I look at this blue triangle and I look at this green triangle, I can move that blue triangle to the green triangle by a series of transformations called translations. And since they map onto each other, these 2 figures would be congruent because the transformation doesn't change the shape. Similarly, I could turn the blue one into a purple one by doing a different transformation, something called a reflection, where again, the shape doesn't change. It's the same shape. They're congruent. Lastly, I could rotate it, spinning that blue one around so it ends up on the red one. And since those shapes perfectly line up, I know that they're congruent. However, it's possible that I could do some other things to the shape by messing with it, stretching it or tweaking it or pulling some things around so that the shapes don't even look congruent anymore. And those are different. Those are not a result of applying rigid transformations. So I know we've already defined congruence as all corresponding parts are congruent, but there is an alternative definition of congruence, which says that 2 shapes are congruent if and only if each part of one figure can be mapped onto the corresponding part of the other figure. Key part here being through a series of rigid transformations. In other words, you do whatever you do to every single point on that shape, and those transformations don't change things. Pro tip, if you're taking the notes, the word missing on this slide is rigid. Put the word rigid in that little box. So there are 4 transformations total that we'll be dealing with. I'm sorry?
Can you go back so I can write that down?
The word is rigid, R-I-G-I-D.
No, like the entire definition.
Oh, no. It's in the notes. The notes are entirely printed out like that. All you're missing is...
I don't have a printer today.
Okay. I would encourage you to not write that whole thing down at all. I've copied this entire PowerPoint and put it in the chat for you. If you want to copy and paste it, you can do that, but there's no point in you writing it all down.
Okay, I'm just handwriting my notes, but okay.
Okay, then I'll ask you to do it from the PowerPoint because it's a Monday. We just won't have time to give you enough time to copy it all down. You could write these down because these are the 4 important ones. So the transformations we're going to deal with are translation, which I like to think of as a slide. It's as though we're on rails. They go left and right and up and down, which a combination of which could be diagonal. But the orientation of the shape doesn't change. In other words, my coffee cup would still be upright. My coffee would still be in the cup if I did a transformation. Excuse me, translation. The second one is a reflection. And depending upon how I did this, my coffee cup could reflect so that it still has coffee in it, or it could reflect the other way where I dump all my coffee onto my desk, right? So there's different ways it could reflect, and we'll talk more about that because it is a flip either laterally or horizontally or vertically. The third one is called a rotation, and that's where we spin something. So for example, let's say I take my calculator here. I could spin it, right? Turn it 90 degrees. Or I could spin it from my elbow, which still spins it. It's just got a longer arm it's spinning from. And those first 3 ones are called rigid transformations because the result at the end stays the same size as the result at the beginning. It doesn't get squished or stretched out. But the last one does exactly that. A dilation changes size. It's the same shape, but a smaller version or a larger version. And if you're taking the notes, the words for this one are flip next to reflection and dilation next to shrinky-dink. These are just little images that show you kind of what they might look like. So a translation or slide is when a shape slides to a new position, left, right, up, or down, and it does not tilt or spin or change its orientation, we're going to be talking about something being in a pre-image state, which is the original state, or an image state, which is the after or the eventual result. Kind of like when you take a picture of somebody, you're taking an image of them. You're not taking the person. The person is the pre-image, and the copy that you make with your picture is the image. You'll notice in the notation, if I take the point A and I make a copy of it, the copy has that little apostrophe on it. That's called prime. So for instance, I copy A and I produce it as A prime. I copy B to B prime and C to C prime, begging the question, who was Optimus? Okay. You'll also notice that the orientation stays the same here. In other words, if I go A, B, C, it goes in a clockwise direction, just like a clock does. And if I go A prime, B prime, C prime, it also goes in a clockwise direction. It retains the orientation. Now, the way we'll be doing this is on a grid. So you'll have a regular XY axis grid, and you'll be given some points, like A, B, C here. And then you'll be given a rule. You see this red rule in there? It says that if you start with points X and Y, and then you're given a rule to take X minus 5 to create your image, and Y plus 1, you just do that to all the X's and Y's. So for instance, the point 1, 2, you'll subtract 5 from the 1, and you'll add 1 to the 2, giving you -4, 3. And then you'll do the same thing to point B. You'll subtract 5 from the X value and add 1 to the Y value, and do the same to point C. And if you plot those new points, what you'll discover is that you've moved all the points in the shape that same 5 units left and 1 unit up. And so the whole shape looks like that. It's certainly possible for you to translate left or right. And the only difference is whether you're saying minus from X or plus from X. And you can go up or down just by adding to Y or subtracting from Y. So in the left-hand picture on the bottom of the screen, you'll see in blue, this is the rule. Eloise, this is what you want to copy. The blue part on the bottom is the most important stuff that you should make sure you get into your notes.
Okay.
If we begin with XY, and then we get a rule that says X plus A and Y plus B, that's a translation. It's the name of it. And we're going A units right and B units left, down, up, B units up, because it's being added to Y. The second one shows X minus A, Y minus B, which means it's a translation, but this time because we're subtracting A from X, we're moving left A units. And because we're subtracting B from Y, we're moving down B units. And for those of you using the scaffolded notes, the part missing in the box is X plus A, comma, Y plus B. Is that enough?
Yeah.
Okay, thanks. So the second transformation we're looking at is called a reflection. And so again, this is just talking high level stuff, no reason to copy this. This triangle is checking itself out in a mirror, right? The vertical black line is a mirror. And as the triangle looks in the mirror, what it does is the eyeball A looks straight into the mirror, perpendicular, and then it looks almost through the mirror to the other side to see its image. And in fact, what's happening is it's going in a perpendicular direction to the mirror, And then it goes that exact same distance on the other side, the virtual side of the mirror. So if you were 10 feet away from a mirror and looking at it, you seeing your own eye would appear as though it's 20 feet away. So for instance, point C would go perpendicular to the mirror, and then that same distance on the other side to create C prime. B would do the same to create B prime. And when you connect them, all of the image would appear to have been flipped, or a mirror image. You'll notice that the orientation has changed. Whereas it used to be A, B, C in a clockwise direction, now it's A prime, B prime, C prime in a counterclockwise direction. But are the shapes still congruent? They are. This is a rigid transformation. We're not stretching it or making it smaller or tweaking it in any weird way. It's just looking at the back side instead of the front side. What this will look like for you guys is, again, we'll be on a Cartesian coordinate system. And this time, when you get a rule for it to be a reflection, instead of it adding and subtracting to x and y, you're going to be multiplying either the x by negative or the y by negative. If you multiply the x by negative, what ends up happening is you just multiply each of the x values by a negative number. And the shape then flips over the y-axis. In other words, everything that used to be a positive x value now flips over to be a negative x value. And so it's a reflection across the y-axis. And this does mess with people, that when I reflect across the y-axis, it's the x value that gets a negative. And if I want to reflect across the x-axis, this is the blue stuff that you should copy down. If I reflect across the x-axis, it's the y that gets multiplied by negative. And I've included the light blue here because it is possible that you reflect, for instance, first across the y-axis and then across the x-axis, a combination of reflections that would result in something still congruent. But I made it a light blue because it's also going to appear for us later as a 180-degree rotation. It's a single transformation of 180-degree rotation, whereas this is a composite of two transformations. For those of you using the scaffolded notes, the first box is over the y-axis, and the second box is x comma negative y. Any questions on this slide? Can I get a check-in, please? 5, this stuff is all very familiar to me. I've done this to some degree in the past, and this makes sense. 3, I've got a little exposure to it. It's sort of making sense, but I need to see some practice before this makes any sense to me. 1, I have no idea what you're doing, dude. This is some crazy stuff. Okay, good, really good scores. All right, yeah, and we will have practice. Tonight, your homework will be very straightforward practice. You'll have 2 images, pre-image and an image on a screen, and you'll say, what was the transformation that got you there? And then you'll have some coordinates for another problem, and it'll tell you the transformation, and you have to apply it to find out what the image would be. Should be very straightforward. So our third transformation is called a rotation. And again, if I hold my hand up here, if you can see my picture, I can rotate my hand at the wrist, and it moves in one particular way. Yes, it changes the direction it's pointing. It's still congruent. It's not losing its orientation. But I could also rotate my hand centered on the elbow. Right? I'm spinning it now with the elbow as the axis. And it's still spinning, but it looks different. So it's really important when we're doing these things that we actually pay attention to and reference the center of rotation. That's where it's anchored around, or its axis of spin. And the way I would spin this, let's say I wanted to go 60 degrees in a clockwise direction, is I would do it point by point. I take point A and line it up with the center of rotation. And then I'd see what 60 degrees from that line looks like. And I'd extend from that center of rotation along that new point the same distance that I had from A to that center of rotation. And that's my new point, A prime. And then I'd go from C to the center of rotation, apply 60 degrees to go up that same distance away at that new perspective to get C prime. Do the same with my B and B prime. And when I connect those, you see that the image is now the entire triangle rotated 60 degrees. This would be a process we could do with our compass and straight edges and a protractor for the degrees. We won't be doing that. Instead, we'll be restraining to use just multiples of 90 degrees because they do it so nicely on the grid. So the first one we'll talk about is that 180 that I mentioned before. If you multiply both the X and the Y by a negative, it is like flipping it over the Y-axis and then over the X-axis, but it ends up being just a rotation of 180 degrees. It's the same shape, spun halfway around the grid. It still has the same orientation. It's still, let's see, ABC in this case, it's drawn to be a counterclockwise ABC. And when I look at A prime, B prime, C prime, the pink one, they don't say prime, do they? Then it's also still counterclockwise. So it retains its orientation. And the rule, which you should write in your notes, is that if you begin with XY, it becomes negative X, negative Y when it's a rotation of 180 degrees about the origin. So when I say about the origin, that's my center of rotation. Any questions on this one? We can also rotate less than 180, but again, we're only going to be doing in multiples of 90. So what's crazy about a 90-degree rotation, this is the oddest one, is if you're looking at my picture right now, my video of my face, you'll see that I've got a calculator holding up and it's in a vertical position, right? It's tall. But if I rotate 90 degrees, it's no longer tall, it's now wide. So things have changed. The shape is still the same, it's still congruent, but in terms of the image, my X and my Y coordinates have traded places. But in addition to that, depending on whether I go left in a counterclockwise direction or right, in addition to swapping places, I have to make one of them negative. So as you see in the rules here, the assumption in geometry is that it's counterclockwise. And if we go counterclockwise, then the X's and the Y's change. And the new X value, which was the old Y value, goes negative. But if I want to go the other direction, 90 degrees clockwise, which is the same thing as 270 degrees counterclockwise, then I swap my X's and Y's, and my new Y value changes. It's negative of what it would have been otherwise. Any questions on this one? Okay, the last one. This is our only transformation that is not rigid. The shapes don't end up congruent. Because what I'm talking about here is a shrinky dink. I'm saying that if I've got a center of dilation, and I always think about, remember shadow puppets? Take a flashlight and you shine it against your hand, you make like an image on the wall of like some wolf or something. So I always picture it that way. Picture that my O, center of dilation, is a flashlight, and I shine it on this triangle. In the far distance on the wall would be the same triangle, but a bigger version of it. In the same way, if I look at those segments created, AO, CO, and BO, and I slice them exactly in half, not like 1 inch in for all of them, but all of them are now half as long as they used to be, and I connect those, it would make a shape that retains the orientation and it retains the scale. In fact, the angles would be the same, but it'll be a smaller size. This is called a dilation. It can be bigger, it can be smaller, and the application of it for what we're doing is really easy. If I say that I'm going to do a dilation with a scale factor of 5 times, it's 5 times as big. All I do is I multiply both the X and the Y by 5. If I want it to be half as big, like this example is here, all I do is multiply everything by 1/2, and it just shrinks the thing down so that it's closer to the origin, and each dimension is now half as large. So again, based on the rule there, if the scale factor is A, you just multiply the A times the X and the A times the Y, and those are your new coordinates. Interestingly, if the A you multiply by is bigger than 1, then your shape is getting larger. If A is less than 1, like a fraction, 1/3 or 1/8 or 2/4, 2/5, whatever it is, then it's getting smaller than 1. The shape is shrinking. I had to put the absolute values on there because of what we talked about with the 180 degree rotation. If I were to say, quote unquote, a scale factor of -3, even though that's less than 1, the image would get larger, but it would also flip down to 180 degree rotation. So by making them absolute values, we're focused just on the dilation. Okay, this is the end of our notes for today. Your homework is big ideas. It's going to give you straightforward examples. Here's an image. Tell me what the transformation is. Then it'll give you coordinates and a transformation rule, and you draw the image. That's pretty much it for today. Please also